So, let's get some physics done to help you pass your exams. This is the Edexcel exam board, but it's the same as AQA, they're very similar. For this exam you'd have 1 hour and 10 minutes, and it's worth a total of 60 marks. Question 1A. Describe a method you could use in a school laboratory to measure human reaction times. Right. That's supposed to be a hand. It's terrible. Hold a ruler. Hold out your 2 fingers. Hold out your finger and your thumb. Get your friend to hold a ruler at the top. Align your finger on the 0 of the ruler, and your friend drops the ruler. They don't tell you when they're going to drop the ruler, and you have to catch the ruler as quick as you can. So make sure that you note the starting point, and then note the point where you grab the ruler. And the difference between the 2 places relates to your reaction time. An athlete runs a 100-metre race. The athlete's velocity is measured at various times during the race. Figure 1 is a graph of the measurements. So it's a velocity time graph. Velocity is in meters per second, times in seconds. Part 1. Draw a curve of best fit starting from 0, 0. There you are. Explain how the acceleration of the athlete changes between 2 seconds and 6 seconds using information from the graph. So during 2 seconds and 6 seconds. So on a velocity time graph, the gradient equals acceleration. The steeper the line, the bigger the acceleration. So if we look at the gradient here and we look at the gradient here, we can see that the gradient is steep at that point, and we can see that the gradient is getting flatter at that point. So steep gradient, it was large acceleration at first, and then flatter gradient equals smaller acceleration. We still know that they are accelerating because the velocity, even at this flat part, the velocity is still getting bigger. Once the gradient is completely flat, that's when there's no acceleration anymore because they're travelling at a steady speed. But it only lasts up to 6 seconds. It doesn't go flat until it gets to 7 seconds. In figure 1, what does the area between the curve and the time axis show? So here's figure 1. Between the curve and the time axis, the area under a velocity time graph tells you the distance that you've travelled. As an athlete runs, a camera travels alongside the track. The velocity time graph for the camera is shown in figure 2. Calculate the acceleration of the camera during the first 2 seconds. So velocity time graph, once again, the gradient of a velocity time graph tells us the acceleration. So they want to know the acceleration between the first 2 seconds. So 0 up to 2. So acceleration equals the change in velocity divided by the amount of time taken for the change. So the change in the velocity, that'll be the final velocity, take away the initial velocity. Well, the initial velocity in this case is 0, so we can clearly see that the change goes from 0 up to 10, so the change in the velocity is just 10 meters per second. And we'll divide that by 2 seconds. That's 5 meters per second, or 5 meters per second squared. Question 2. Iodine-131 is a radioactive isotope. The symbol for a nucleus of iodine-131 is shown in the figure 3. The number 53 in the figure is that's the atomic number. If it did ask for the top number, that would be the mass number. Iodine-131 decays into an isotope of xenon by emitting beta minus radiation. Complete figure 4 for a nucleus of this isotope of xenon. So what it's saying is it starts as 131 iodine and it's going to turn into xenon plus a beta minus radiation. Now remember, beta is an electron. Electrons have got 0 mass, that top number is the mass number, and the bottom number is the charge number. So beta minus has got a charge of -1. Now whatever this number is on the bottom, on the left hand side of the arrow, it has to equal this number on the bottom, on the right hand side of the arrow, added to this number, which is on the bottom of the right hand side of the arrow. So that plus that equals that. Now what have you got to add to -1 to make 53? You have to add 54. So 54 plus -1 equals 53. Now what have you got to add to 0 to make 131? Well, you've got to add 131. 131 plus nothing equals 131. So that number plus that number has to equal that number, and that number plus that number has to equal that number. Iodine-131 has a half-life of 8 days. Explain what is meant by half-life. So half-life, it's the time taken for the activity to half. Or you could say it's the time taken for the number of radioactive nuclei in the sample to fall by half of the original value. But I much prefer the top explanation, it's a lot easier. Part 2. A sample of radioactive material contains 10 grams of iodine-131. Calculate the mass of iodine-131 remaining after 24 days. Well, it said that the half-life was 8 days, which means that every 8 days the activity or the amount of material you've got is going to half. So we need to calculate the mass left after 24 days. So how many times does 8 days fit into 24 days? And then we'll be able to work out how many half-lives we've had. So 8 days into 24 days equals 3 half-lives. So that means it's going to half 3 times. So we're starting with 10 grams it's going to half once to 5 grams. Then it's going to half again to 2.5 grams. And then it's going to half again to 1.25 grams. And that would be, so at 0 days, you'd have 10 grams. 8 days later, you'd have half of 10 grams, which is 5 grams. Another 8 days later, which would be 16 days, you'd have halved again. And then the full 24 days, it would have halved one more time. So your answer is 1.25 grams. And I always like to set it out like that. It just makes things visually easier to understand. Part C. Figure 5 shows a Geiger-Müller tube detecting the beta-minus radiation coming from a radioactive source. So that's the radioactive source emitting the beta-minus particles, and they're going into the Geiger-Müller tube, which is detecting the radiation. Devise a plan to test whether a 5mm thickness of aluminium is enough to absorb all the beta-minus particles from this source. And it's worth 2 marks. So what you want to do is first of all remove the source out of the way and measure what's called the background radiation. The background radiation is around all the time, so it might have 5 or 6 clicks per second. So that's without the source being there. Now, place the radioactive source next to the Geiger-Müller tube and record the size of the radiation. Now, if you place the 5mm thickness of aluminium in the way, if the count decreases right back down to the background level, then you know the 5mm thickness of aluminium was enough to completely stop the radiation from the radioactive source. And there we go. That's actually enough to get 3 marks rather than just 2. So that is a good way to structure any question to do with this particular concept. Question 3. Describe in terms of air particles how a sound wave travels through air. You may draw a diagram to help you answer. So a sound wave is a longitudinal wave which means the energy travels parallel to the vibrations of the air particles. Or if you don't think you can remember saying that they vibrate parallel, just say that the air particles vibrate in the same direction to the direction that the energy is travelling. Part B. Which of these could give you a measure of the loudness of a sound? So the loudness of the sound depends on how far up from the middle section or how far down from the middle section. So that's what we call the amplitude. And this middle section here is what we call the position of zero displacement. It basically means if the wave's got no energy, it's just a flat line. Imagine waving some rope. If you just had the rope flat at first, then there's no energy. As soon as you start to wave the rope a little bit, it's a little bit of energy. If you wave the rope a lot, then it's a lot of energy. So a wave that goes up and down more, in other words, a bigger amplitude, that means it's got more energy. And if a sound's got more energy, it's louder. So the loudness of a sound is the energy of the sound, and that's represented by the amplitude. Part C. Two students, M and M, do an experiment to measure the speed of sound. Figure 6 shows part of their experiment. So M and N, they are the students. They're standing 100 meters away from a large smooth wall. The students stand 100 meters from a large smooth wall. Student M claps his hands repeatedly. Student M makes sure he claps at the same time that he hears the echo of his previous clap. So in other words, student M is going to clap his hands. The sound's going to go to the large smooth wall where it's going to echo off the wall and it's going to come back. Now when he hears it come back, he's going to clap his hands again, in which case he's going to send another sound wave out and it's going to reflect again. So every time he hears the echo, he claps his hands. Describe how student N can measure the time for the sound to travel 200 meters. Now it's saying 200 meters because that's obviously 100 meters to the wall, and then the echo is going to come back another 100 meters, so that's 200 meters. So he's going to, if he starts his stopwatch when he hears person M start his clap, and then if he stops his stopwatch when person M claps again, because that means that his clap has travelled, the sound from his clap has travelled 200 meters. Now that is going to be a very short amount of time, so he's probably best to time 5 claps, let's say, and then divide his time by 5. And then divide the total time by 5. Explain one way the students could improve the accuracy of their experiment. Well, sound travels at roughly 330 meters per second in air. So to travel 200 meters is going to be less than 1 second. So if we make the wave travel further, then it'll take longer for the wave, and that'll make it easier to use your stopwatch to time the wave. If we hadn't already said record the time for 5 claps, you could say that down here. Instead of just recording the time for 1 clap, record the time for 5 claps. Explain why the wall should be large and smooth. Sound echoes off large, flat surfaces. If it's large, that means you'll get a large amount of the wave being reflected, and hopefully it should be loud enough to hear. And the wall should be smooth so the reflection comes straight back to you. The reflection of sound comes straight back to you. In other words, the echo comes straight back to you, rather than being scattered all over the place, which would make it harder to hear. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.